Diamonds. 4 billion years old, and they still dazzle us. But these rocks aren't just for show anymore. Hidden inside are powers that could change your life.
The future of diamond is very exciting and opens up what many of us have been calling the new diamond age.
To reach that shining future, scientists have to outdo nature and build a better diamond.
The new synthetic diamonds, that's a technology that's going to take us places we've never been before.
It's a dazzling challenge. Can science do the unnatural and make a super diamond? Diamonds are like no other substance. They're 4 times harder than any mineral on the planet. They resist corrosion. The best are completely transparent. And they conduct heat. Some can conduct electricity.
What you have is a material such as diamond that has a fantastic range of unique properties, and it's the combination of these unique properties that makes diamonds special.
If science can harness the powers of these stones, it could revolutionize our lives. From the microchips in our phones to the machines that explore space.
They'd be super durable, they'd last forever. They'd be resistant to heat and cold and the other kinds of extremes.
It's said diamonds are forever, but they aren't. Most contain natural flaws, flaws that can't withstand extreme heat and pressure. To transform technology, science must do something unnatural. Create the ultimate diamond in the lab.
Nature is the guideline, and the question is, can we improve upon it? The race now is to produce a super diamond.
A super diamond would have all the properties of a natural diamond, but could be manufactured in any shape or size. Most of all, they would mimic the properties of the rarest gems, like this one. The Hope Diamond. Perhaps the world's most perfect natural diamond. It's kept behind bomb-proof glass in the Smithsonian Institution in Washington, D.C. At 45.5 carats, this gem is over 100 times bigger than the average diamond ring. It's one of the largest and most valuable diamonds ever discovered, worth around $250 million. But that's not all. This gem has some unusual properties that highlight what makes diamonds so special. Jeffrey Post, the curator of the National Gem Collection, is researching this stone. In the lab, he demonstrates a phenomenon that sets the Hope Diamond apart from most others.
We can take an ultraviolet light and we can expose the Hope Diamond to the ultraviolet light, and we'll leave it on for about 10 or 15 seconds. Also notice that one of the white diamonds on the outside fluoresces very bright blue. And so now we're going to turn the room lights off, and I'll turn off the ultraviolet light, and we can see the intense orange glow, the property called phosphorescence.
For years, this glow was attributed to a curse cast over the diamond when it was stolen from an Indian temple centuries ago. But Post isn't superstitious.
So here you've got supposedly a cursed diamond that glows this blood red color. Well, you know, that's a great story in itself. But then the scientist in many of us says, well, why does it do that?
Post and his team investigate using a spectrometer, an instrument that analyzes wavelengths of light. The spectrometer shows that the Hope's distinct hue comes from two colors: aqua and red. The team can now identify two chemical elements in the diamond: boron and nitrogen.
Suddenly, now I understand what is going on when this diamond is phosphorescent.
Boron makes the stone blue. When combined with nitrogen, the stone shines red. Chemicals, not a curse, make the Hope glow. It's not the red glow that excites scientists, but the element that makes the Hope blue: boron. Boron does more than color diamonds. It also allows them to conduct electricity.
Blue diamonds, because of the boron present in them, are in fact semiconductors of electricity, which makes them very different than other diamonds that are pure carbon.
Pure white diamonds are electrical insulators. Try to pass a current through them, and nothing happens. But blue boron-rich diamonds, like the Hope, are electrical conductors. The extra atoms of boron interact with the existing diamond atoms, letting an electrical current pass through. But all diamonds, not just blue diamonds, have another useful property. They transfer heat better than any material known. If science could make synthetic diamonds that both conduct electricity and transfer heat, they could revolutionize a critical component of daily life: the semiconductor. Semiconductors are the vital component in nearly every electronic device. In transmitting electricity to the precision control of microchip technology. For the past 50 years, these devices have been made almost exclusively from silicon. But silicon has a major drawback. The more electricity it carries, the hotter it gets. The result? Most silicon chips require complex cooling technology. If they exceed about 300 degrees Fahrenheit, they'll shut down.
One of the huge hurdles that are facing manufacturers is that they have to be able to remove the heat away from these electronic systems. You know, think of your own laptop at home as you're operating it. It gets hot. And so this becomes a big problem. Right now they're using metals mostly to do that. But diamonds, in fact, are much better conductors of heat than metals are.
With the discovery that blue diamonds transfer heat and conduct electricity, scientists can imagine the unimaginable. A world beyond silicon. A world where everything from your cell phone to a spacecraft runs on diamonds. Diamonds can carry 30 times more power than silicon and operate 3 times faster. And they're so efficient at transferring heat, they could run a computer at speeds that would melt a silicon chip. They also resist temperatures over 1,800 degrees Fahrenheit.
To be able to coat electronics with diamond or use pieces of diamond as the heat sinks would certainly offer a whole new direction for the manufacture of even smaller, more powerful electronic devices.
Despite their eye-catching sparkle, diamond's real potential has been overlooked for centuries. The possibilities for technology are almost endless. But there's one problem. Diamonds are rare and expensive. Natural semiconducting diamonds like the Hope are thousands of times more rare. And they don't come in the right shape or size for industrial use. So scientists are trying to create a synthetic superdiamond with all the powers of a natural blue diamond, but in a size and shape of our design. To succeed in creating a superdiamond, scientists must first discover how nature made hers. And for the answer, they look to the stars. For scientists to create a synthetic superdiamond, they must first get back to basics and investigate the ingredients of a natural diamond. For all their rarity, diamonds are made from one of the most familiar elements on Earth, carbon. Carbon is so fundamental, it forms the basis of everything around us. Even we are 18% carbon. It's so common, it's estimated that our planet contains over 100 million billion tons of it. But carbon doesn't originate on Earth. It comes from long ago and far away. A star on the brink of death. A red giant. Astrophysicist Neil deGrasse Tyson studies carbon's dramatic formation.
Well, the universe is born without any carbon. Our sort of birth ingredients are hydrogen and helium and just trace amounts of lithium. So carbon comes later. Carbon is forged in the cores of stars.
This red giant star once looked like our sun. But as it ages, it grows over 1,000 times bigger. Instead of glowing white hot, it glows red as it reaches the end of its life. It's running out of fuel. Its core is now composed almost completely of helium. In its death throes, a nuclear reaction in the core breaks down helium and fuses it together in a new configuration, carbon. Dying red giants are the universe's carbon factories. Eventually, the star explodes in a white-hot flash, so strong that billions of tons of carbon are flung out into the farthest reaches of space.
What happens is the star collapses, and the entire core, in response to this collapse, rebounds and explodes. A titanic explosion we call a supernova. And its guts are scattered everywhere. And it's a spectacle. It's so much of a spectacle that you can see these stars explode halfway across the universe.
In time, the vast cloud of debris from the explosion is pulled into orbit around a new star. As this debris spins, it clumps together. Over millions of years, these clumps grow, and planets begin to form. This is how our solar system and our planet itself was born. And it's why Earth holds the raw ingredient for diamonds, buried deep in huge quantities: carbon. For scientists hoping to create a superdiamond, a problem. The form carbon usually takes is weak. Carbon in its most familiar form is graphite. Great for pencils, but far too soft for high-tech products. Bob Hazen, research scientist at Washington, D.C.'s Carnegie Institution, is an expert on carbon and diamond formation.
You know, it's amazing. Diamond and graphite are made out of the same element, carbon, but they're so vastly different. Graphite has these planes of weakness, and you can see how every one of these black dots, the carbon atoms, are connected to 3 other carbon atoms in a triangle. But in diamond, Every carbon atom is now connected to 4 adjacent, and this trellis, this network, this lattice. So diamond is strong in every direction. That's the difference.
For scientists hoping to create a super diamond, making it hard will be tough. They have to recreate a diamond's lattice-like structure. To do that, they have to figure out how nature turns basic carbon into a dazzling diamond. Scientists are on a quest to figure out how to make a super diamond. Their search begins here, South Africa, diamond capital of the world. Diamonds were discovered in these rocks in the 19th century. Hundreds of thousands have been mined here, but only recently did scientists learn how they actually formed. Professor Steve Haggerty is an expert on how diamonds are created.
Diamonds were a real mystery in terms of their origin. They were found in clusters. So you found one diamond, and by golly, there would be others to be found as well. So that led to the notion that the process in which the diamonds were brought to the surface was possibly deep.
Diamonds form deep within the Earth in an area called the mantle, the layer between the Earth's crust and its superheated core. Down here, intense pressure changes the molecular structure of carbon by crushing its atoms together and forcing them into a new lattice-like structure. Under extreme pressure and temperatures, carbon becomes diamonds.
The temperatures have to reach about 1500 degrees centigrade and the pressures about 50 kilobars.
That's 2,700 degrees Fahrenheit and the weight of over 4,000 grown men standing on your foot. The journey from a dying star to a diamond mine is almost complete. 100 miles still remain between their source in the mantle and the Earth's surface. Luckily, they're fast-tracked to the surface by a substance called kimberlite.
Kimberlite is a rock, it's the host rock to diamonds. Even though the diamonds do not form in the rock, it's the transporter.
Kimberlite is a volcanic rock that forms deep within the Earth. As it moves to the surface, it creates a carrot-shaped pipe filled with molten rock, mantle fragments, and diamonds. When it breaks through the crust, it erupts in small but violent volcanoes.
I like to think of these as volcanoes of opportunity. These rows, they picked up the diamonds from their safe deposit boxes deep in the earth, about 200 kilometers down, and then were explosively erupted.
At the surface, magma builds up a mound of volcanic material that eventually cools and hardens. Hidden within the rock are diamonds, incredibly rare, perfectly formed crystals surrounded by kimberlite. Rarer still are blue boron-rich diamonds, like the Hope. Less than 1 in 100,000 form this way. "4 billion years from a dying star to the Earth's surface. Yet in a matter of days, scientists aim to turn raw carbon into super diamonds."
In order to produce anything of that nature, it would require extraordinarily high temperatures and pressures. It turns out that it's not very easy to transform graphite into diamond.
The attempt began in the 1950s, when General Electric launched Project Superpressure. Their goal, to create the first synthetic diamond. They develop machines to crush graphite at nearly 800,000 pounds per square inch and heat it above 2,500 degrees Fahrenheit, replicating the very forces in the Earth's mantle. It takes 5 years and millions of dollars, but finally, in February 1955, GE announces they've done it. The world's first synthetic industrial diamond. Over 50 years later, just outside Johannesburg, South Africa, a lab called Element 6 continues the quest for synthetic diamonds. Following GE's lead, they synthesize diamonds on a mass scale, not for jewelry, but for heavy industry. Scientist Richard Botkin is a pioneer of industrial diamond research.
We have banks and banks of presses that are capable of producing diamonds in no fewer than 45 minutes. To see such technology room after room is absolutely amazing.
The diamonds they produce start as a highly pure form of graphite powder. It's baked inside a pressure chamber between 2,500 and 3,600 degrees Fahrenheit.
Effectively, you're stacking 20 sedan motor cars on it and heating it between 1,400 and 2,000 degrees Celsius.
The result is a diamond 50% harder than those found in nature. And Element 6 can produce handfuls. These diamonds have revolutionized the drilling and mining industries. The friction from drilling into hard rocks, like granite, generates high temperatures that can damage ordinary drills. But diamond tip drills transmit heat away from the drill tip.
Oil and gas drilling benefits immensely from diamonds simply because we can drill faster and deeper with diamonds.
One shortcoming: industrial diamonds are small. The next challenge is to create diamonds large enough to be printed with circuit boards or shaped into other high-tech devices. It's a challenge that the Sarasota, Florida company Genesis is tackling. Using a special machine, they actually grow large diamonds. They start with a seed, a microscopic diamond, either natural or artificial, and surround it with graphite. It's a delicate process that shows how hard it is to create large diamonds. In charge of the process is Chief Operating Officer Clark McEwen.
We take graphite and we put it along with an actual diamond seed into an environment that emulates what happens within the Earth.
These two forms of carbon, the diamond seed and the graphite, are placed inside the chamber, where they're heated and crushed by a powerful hydraulic press.
As you apply that temperature and pressure, what happens is that graphite turns into individual carbon atoms. And those atoms permeate down and it finds that diamond seed and it attaches to it. It acts as a template.
As the graphite melts, it releases carbon atoms, which crystallize on top of the diamond seed. Molecule by molecule, the diamond grows. What nature does in 4 billion years, they do in 4 days. The result? A large artificial gem, up to 3 times larger than the seed. With this breakthrough, scientists can now consistently make large diamonds. But the real breakthrough that scientists need is yet to come. Genesis can't grow diamonds in the shapes needed for high-tech use.
We haven't gotten there yet, but we're constantly working on improving the process and making larger and better quality diamonds.
Scientists are trying to create a large diamond with all the properties of a real diamond, but in shapes and sizes not found in nature. From circuit boards to scalpel blades, the uses could be endless. As scientists struggle to perfect the diamond, a clue hurtles toward Earth from an unlikely place. After years of research, scientists discovered how to make gem-sized diamonds. One hurdle remains to making a true super diamond, making them in any shape and size. Science needs a breakthrough, and it comes from space. These strange objects look like burnt stones. They've been found in South America and Central Africa. Tests reveal a surprise. The stones are actually diamonds, black diamonds.
These are two of the famous black diamonds called carbonado because of their similarity to charcoal.
Carbonado has been known for centuries, but how it forms remains a mystery. Only recently has its potential value to science emerged. George Harlow of the American Museum of Natural History is investigating what makes carbonado so special.
Carbonado is a conundrum because it doesn't have the characteristics that we associate with diamonds that formed in the mantle on Earth.
Diamonds originating in Earth's mantle form under immense pressure and high temperature, so they're compact and dense. Not black diamonds. Using a microscope, scientists find they're riddled with holes.
It's got a lot of void space in it. Now, deep within the Earth, the void would have to be filled with something. Well, the something ain't there.
Normal diamonds contain very little void space. As they form deep in the Earth, they're crushed into a single crystal. Carbonado seems to form differently. Unlike normal diamonds, it's composed not of one crystal, but millions, all linked together. Scientists conclude carbonado formed not under high pressure, like normal diamonds, but low pressure. But just where does carbonado come from? Once again, research leads to the last gasp of a dying red giant.
The current theory for the origin and genesis of carbonado is that the small diamonds formed in supernova explosions.
Haggerty believes the vacuum of space explains carbonado's unique structure.
The diamonds were hot, one diamond bashing into the other, and they finally became glued to form a larger diamond.
During its explosive formation, specks of mineral dust are also trapped, making the large diamond appear black. The diamonds are then transported to Earth by a meteorite.
When the meteorite hit, it showered diamonds, so this must have been a truly amazing sight, with carbonado diamonds being liberated from the meteorite on impact.
It's not just the large size of space diamonds that fascinate scientists. Carbonado has another advantage over regular diamonds. Its multi-crystal structure makes it not only larger, but tougher. It's almost impossible to cut. Not so a natural diamond. Although it's one of the hardest materials known, it has its weaknesses.
You know, diamond's incredibly hard, but it can be broken along certain planes. They're called cleavage planes. And it just happens that there's certain directions in diamond where there are fewer strong bonds, and that's the direction the diamond opens.
A natural single crystal diamond will split cleanly where its chemical bonds are weakest. By following this cleavage plane, a gem cutter can split the stone perfectly. For scientists, this weakness in single crystal diamonds is a fatal flaw. Diamonds that might fracture aren't durable enough for high-tech use. The key to making a tough super diamond lies in replicating Carbonado's multi-crystal structure. Their theory of how Carbonado forms in the vacuum of space yields another breakthrough. A whole new way to make diamonds.
The space diamonds have now taught us that, in fact, we don't need pressure at all. This can be done in a vacuum.
Carbonado sets the stage for a new kind of super diamond. One tougher and larger than ever. That can be made into multi-crystal shapes not found in nature. The key is using low pressure to simulate the vacuum of space.
How do you make a diamond in a vacuum when diamond's only stable at high pressure? And the way you do it is by fooling the carbons into being so energetic, so excited, that when you cool them down, they find a more stable configuration. And the first one they find is diamond. And they don't go any farther.
This process is called chemical vapor deposition, CVD for short. It begins with a tiny diamond seed sealed inside a vacuum chamber slightly below atmospheric pressure. The chamber is heated to 3,600 degrees Fahrenheit. Then methane, a carbon-bearing gas, is pumped in. Then hydrogen. The gases are bombarded with microwaves, which agitates them, forcing the hydrogen and methane molecules to collide. This process releases a cloud of carbon atoms that settle on the seed, and gradually, the diamond grows. This was the seed they started with. 24 hours later, it doubles in size. At the U.S. Naval Research Laboratory in Washington, D.C., James Butler is taking this CVD process to the next level. They're growing not single stones, but wafer-thin diamond sheets.
One of the materials we grow starts with a non-diamond material, for example, a silicon wafer, onto which we put a very thin layer of these little diamond seeds. Think about shaking salt onto the kitchen table and having a whole bunch of salt crystals there. And then we put them in the CVD environment, and they will grow. And as they grow together, they bump into each other and they become this mass. So it's all diamond, but with many different grains of different orientations.
Each diamond crystal bonds to another to form a mesh of crystals across the wafer, less than a 50th of an inch thick. They can be made up to 8 inches wide. The shape of the template determines the shape of the diamond sheet. Perfect for making a wafer to replicate silicon. They're much tougher than natural diamonds. They conduct electricity and resist extreme heat. These are true super diamonds. super diamonds have been filmed with image intensifiers that show how much more efficient diamonds are at conducting heat than the copper traditionally used in electronic components. The left plate is made of synthetic diamond. On the right, copper. The two plates are placed in ice and attached to a thermal image intensifier, which records heat as it travels through an object. As the diamond plate on the left shows, it conducts heat faster than copper, up to 5 times faster. It's this unparalleled quality that puts the super in super diamond. Scientists are excited. For the first time, they have a material that could challenge the domination of silicon. Microchips made from diamond wafers can run electronic devices at higher speeds and with more power without overheating. Faster, smaller, and more efficient. Razor-thin computers, long-lasting cell phones, and picture-perfect TV screens.
I think the future of diamond is very exciting. Particularly, I think CVD diamond opens up what many of us have been calling the new diamond age.
Electronics are only the beginning. Today, scientists can make diamonds in shapes and sizes for uses that could revolutionize tomorrow. Researchers at the Carnegie Institution in Washington are trying to solve some of science's biggest mysteries. From how compressed gas can conduct electricity to how microscopic life can survive in extreme conditions. These investigations need extremely high pressures, which they create using a powerful vise called a diamond anvil cell. It squeezes an object between 2 diamond tips, creating a tiny environment of high pressure between them. It can recreate forces as extreme as pressure in the center of the Earth. For the Carnegie team's experiments, this wasn't extreme enough. But when they pushed the pressure higher, they hit a snag. The diamond shattered. Russ Hemley, director of the Geophysical Lab, decided to upgrade the anvil by making an ultra-hard super diamond.
Well, our group has been very interested in using diamond for high-pressure experiments for many, many years. And we basically needed to take this to the next level. We needed better diamond, stronger diamond, larger diamond than could be provided by Mother Earth or from conventional processes.
To create his super diamond, Hemley used a version of the CVD method to speed up the growth rate. The team then exposed the crystals to a high-pressure, high-temperature treatment to further harden them. The result? Another leap forward for super diamonds. The diamond not only grew many times faster, it also grew bigger. 15 carats. In just 6 days, they'd created a stone 1/3 the size and 50% stronger than the Hope Diamond. A gem that took nature billions of years to forge. The new super diamond was so tough, it broke Hemley's hardness gauge. When used in the diamond anvil, this new super diamond proved the breakthrough he needed.
This can produce pressures that are millions of times the pressures found at the surface of our planet.
Now, he can simulate forces so extreme they've never been studied before. Like those deep in the Earth's mantle, where pressures reach up to 1,300 kilobars. That's nearly 20 million pounds per square inch. This improved instrument lets Hemley study some of our biggest questions, like is there life in outer space? Hemley's team takes 2 common strains of bacteria, including E. coli. They place them in a liquid and crank up the superdiamond anvil. The liquid turns into a dense form of ice. Under the intense pressure, most of the bacteria are destroyed. But incredibly, 1% survive. If bacteria can survive these harsh conditions, maybe life exists in outer space, perhaps on other planets. Thanks to superdiamonds created under low pressure, diamonds will reshape the future. Superdiamonds will change communications everywhere, especially on the battlefield. In constant use and battered by the elements, equipment like radios often break down in the harsh conditions of combat. But imagine if they were made of superdiamonds. Already, they can be shaped into tiny sound transmitters called nanoresonators, making vital radios and computers more robust and efficient. They can vibrate up to 100 billion times per second to create the highest quality sound yet achieved. Yet, they're tough as nails. All this from a diamond 1,000 times smaller than the width of a human hair. It's not just soldiers who will benefit. Diamond resonators will eventually be used in everyday devices like cell phones, allowing longer talk time and crystal clear reception. The same sparkle that attracts us to diamond jewelry reveals another of its secrets, its clarity.
It's transparent to light. It slows down light that passes through it.
As light enters a diamond, the dense carbon structure slows it down to less than half its normal speed. As it reflects inside the stone, the light appears to hang around longer.
You can actually force light to completely internally reflect and come out at some other angle. That's why diamonds look radiant, because light comes in from one direction, comes out another. It makes you think it's generating its own light, but it's not. All it did was redistribute the light coming in from other angles. It's remarkable.
Now you know why diamonds sparkle. The unique optical clarity of diamond, the perfect material for high-tech optical uses. Diamond is transparent across a huge spectrum of light, from ultraviolet to infrared. It's the only substance through which light passes virtually unaltered. From superdiamonds, NASA can make super hard, super clear windows. The possibilities for superdiamonds are endless. Soon, you may find a diamond everywhere, from your desk to your galaxy.
The future of diamond, we're just seeing the very beginning of it, and I mean the stars are the limit when it comes to what we're going to be able to do with diamond in the future.
Nature took billions of years to perfect the diamond. Now, we make super diamonds in days. Tougher, bigger, and better.
The new synthetic diamonds, that's a technology that's going to take us places we've never been before. It's going to take science in new directions. It's going to allow us to do things we could never do before. So the natural diamond, we treasure that as an object. The synthetic diamond, that will give us knowledge.
Like steel, transistors, and silicon, synthetic diamonds could revolutionize life. Welcome to the age of super diamonds.